In this problem, we are to construct a microwavable cup of soup in the shape of a cylinder, and that cylinder must hold 450 cubic centimeters exactly. We can make the cylinder in many different ways. For example, it could be short and wide, or tall and skinny. But there's only one way that will minimize the production cost of the package. It is given that the sides and the bottom of the container will cost 4/100 of a cent per square centimeter. The top costs 5/100 of a cent per square centimeter. Our goal is to find the dimensions, that means the radius and the height of the cylinder, that will minimize the production cost. So to find the minimum cost, the first thing we must do is to write a cost formula and then minimize it, subject to the constraint that it must hold exactly 450 cubic centimeters of volume. Because the cost was given in cents per square centimeter, I'm going to measure the radius and the height of the cylinder in centimeters. First, let's go through some formulas that we'll need to solve this problem. The volume of a cylinder is given by this formula here. To show where that formula comes from, anytime you have an object that has a constant cross-section, so for example, anywhere I cut this cylinder horizontally, its cross-section would be a circle. Here I show that cut being made towards the top of the cylinder, but even towards the bottom, if I were to slice horizontally, I would still get a circular cross area. So to find its volume, I simply take the formula for the area of a circle, which is pi r squared, and multiply by its height. So notice the volume is pi r squared, which is that cross-sectional area, and then you multiply by the height, and you'd get the volume of the cylinder in cubic centimeters. The last formula for the area of the top and the bottom, that surface area is nothing more than the area of a circle, which we've already said is pi r squared. To show where the area of the side of the container comes from, I'll use this diagram to the right, where I argue that the surface area of the side of the cylinder can be found by taking the can, slicing it vertically, let's say about this black vertical line, unwrapping the can, and what you'd get is a rectangle. If it's difficult to picture how this would play out, imagine going to your pantry and taking out a can of soup. I actually did this. Then I took scissors, cut the label of the can vertically, literally unwrapped the label, and you can see that over here. Because of the angle of my cell phone camera, it may not look quite like a rectangle, but of course it is. You can also picture that the distance around the circle that I'm drawing here, which is the circumference of the circle, 2 pi r, would become this dimension over here on the rectangle. So that would be 2 pi r. Of course, the height of the label would not change. So once you can visualize that unwrapping a soup can label turns that cylinder shape into a rectangle, I can argue that the surface area of the side of the cylinder would be the distance around this circle, 2 pi r, which became this dimension, that will be in centimeters, and the height of the cylinder would remain unchanged. It would be the same as the height of the rectangle, which is also in centimeters. And of course, the area of the rectangle is just the length times the width, so that would be 2 pi r times h, and then of course centimeters times centimeters would give you centimeters squared. So that's the formula for the area of the side of the cylinder in square centimeters. All that being said, we're ready to construct our cost function. The cost of the top would be its area, which was pi r squared, times the cost per square centimeter, which was given to be 5/100 of a cent per square centimeter. So this is my area, which was in square centimeters, and I multiply that area by the cost per area, which was 5/100 of a cent per square centimeter. Notice that the units work out. Centimeter squared here cancels with centimeter squared here, and this would be the cost of the top in cents. So remember, the cost of the top is 0.05 pi r squared cents. We'll need this in a minute. The cost of the bottom would be very similar, because the bottom of the cylinder was also a circle whose area would be pi r squared centimeters. And if you took that area and multiplied by the cost per area, which was 4/100 of a cent per square centimeter, again, square centimeters cancel, and you get that the cost of the bottom of the container in cents would be 0.04 pi r squared cents. And we'll need this in a minute as well. Finally, we can calculate the cost of the side of the container by taking its area, which was given to be 2 pi r h, and because both r and h are in centimeters, you get centimeters times centimeters is centimeters squared, so that checks out. And if you take that area and multiply by the cost that was given to us at the beginning of the problem, which was 0.04 of a cent per square centimeter, once again, you get the square centimeters cancel, and you get the cost of the side in cents. So let's simplify that first by saying that 2 times 0.04 is 0.08, and then we have pi RH, and that cost is in cents. Now that we have the cost of the top, bottom, and side of the container, we can add them all together to get the total cost. So the total cost was 0.05 pi r squared for the top. Add that to the cost of the bottom, which was 0.04 pi r squared. And then finally add the piece we just found, which was 0.08 pi r h. And since all three of those costs are in cents, the total cost would be in cents as well. Let's simplify our cost formula before we minimize it. We have these two like terms can be combined to give us 0.09 pi r squared. Copy the last term. Now this equation for the cost could not be minimized if it were not for our constraint. If you remember, the volume of the cylinder, which is pi r squared h, had to hold 450 cubic centimeters of volume. Now currently my cost function is a function of both the radius of the cylinder and its height. In order to eliminate the variable h, what I can do is take the equation for volume and solve for h by simply dividing both sides of the equation by pi r squared. Because h is 450 divided by pi r squared, I can replace this h in the formula with that algebraic expression. So here I literally copied the equation, but where I see the letter h in the equation, I'm going to replace it with 450 divided by pi r squared. So I'm doing that now. And now notice my cost function, as promised, is now only a function of the radius of the cylinder, now that we eliminated the variable h. I'm going to simplify my cost function by noticing that 0.08 times 450 is simply 36. Also noticing that the pi's simplify out. Pi divided by pi is 1. And this r cancels with one of the r's in the denominator here. So I'm left with 36 divided by r. I'm going to find the minimum cost using my graphing calculator. So I've pressed y equals on my calculator, and I'm just going to type out my cost function. So notice where I see y sub 1 in the calculator, that represents my variable c for cost. To get pi, I hit second caret, and then I have to use the letter x to represent the radius of the cylinder. The most difficult thing about the calculator when graphing is finding a good window. Obviously my radius, which I'm denoting as x, has to be positive. So pressing window, it makes no sense to have my x min at -10, because you can't have a negative radius. At the very minimum, it could be 0. I'm going to leave this at 10 for the time being. So right now, my radius can be as small as 0 and as big as 10. I also recommend changing the y min, which, remember, the letter y is representing the output variable, c in my problem, cost. The cheapest something could be is 0 cents. Not knowing how big to make the y max, what you can do is leave it alone for a minute. I'm going to hit graph, and you shouldn't be concerned, even though I don't see the graph. If I press trace, you'll see, for example, one point on the graph would be when x is 5, which means the radius is 5 centimeters, my cost would be about 14 cents. So notice my y value is already outside that window because my y max was 10. If you want to press to the right and see exactly how costly this can become, you see as I trace to the right, we quickly get into 18 cents, 19 cents, etc. So I'm going to go back to my window, and I'm just going to guess that for radii between 0 and 10 centimeters, the cost would be between 0 cents and, say, 30 cents. I'll press graph again. This time you can see the function graphed, and you can clearly see a minimum. I'm going to use the min feature on my calculator to find the radius that minimizes the cost. So I'm going to press second key, the trace key. Notice that the minimum feature of the calculator is number 3. You can either press 3 or scroll down and press enter. It will ask you 3 questions. First, it's asking for a left bound, which simply means it wants you to trace to the left so that you're to the left of the minimum. To trace quickly, you can press second left, and that'll be a little faster than just pressing the left arrow one time. Now that I can see that my cursor is to the left of the minimum, for example, my minimum is right here, my cursor is to the left of the minimum, I press enter to define that as a left bound. Now to do a right bound, I do a similar thing by pressing second right arrow to efficiently move to the right of the minimum. So now I can see that my cursor is to the right of the minimum, which appears right here. I'm going to press enter to define that point on the curve as a right bound. So now the calculator knows to look between these two vertical dashed lines in blue to find the minimum, and I can see that my minimum is contained in that region. The calculator wants you to guess what the minimum is, but it turns out you can be a bad guesser and just press enter. It will still find it. So for example, it's finding that you'll get the minimum cost when x, which is really r, when the radius of the cylinder is 3.9929 centimeters, and the minimum cost would be the y value here, 13.5 cents. So let me write these numbers down. We have to minimize the cost, the radius needs to be, to 4 decimal places, 3.9929 centimeters. The minimum cost, the calculator said, is going to be approximately 13.5239. If you look at the 4th decimal, it was an 8, but the next digit was a 5, so I rounded the 8 to a 9. Remember that the cost is in cents, so this would be the minimum cost. So remember, the original problem actually wanted the dimensions that minimize the cost. So now I have the radius of the cylinder that would minimize the cost, but the other dimension of the problem would be the height, which was 450 divided by pi r squared, and we just found that the r value that minimizes the cost is 3.9929 centimeters, and that's being squared in the formula. So all I've done here is replace r with 3.9929 in our constraint function. Let's type that out to find how many centimeters the height of the cylinder needs to be to minimize the cost. You may not know this about your calculator, but because the last x value that I had on my screen was that 3.9929, if I hit second quit and simply type the letter x, you'll see that the calculator has that number stored into x. So now I can simply type 450 divided by parentheses pi, which I get from second caret key, and because I have the radius stored in for x, I can simply press x squared instead of r squared, right parentheses, enter, and I get approximation for the height of the cylinder to 4 decimal places that minimize the cost would be 8.9841 centimeters. Knowing the correct radius and height allows me to properly construct the cylinder that minimizes the cost, and it's also nice to know roughly what the cost of each soup container is going to come out to be, which for us is roughly 13.5 cents. It's important to note that when I used the letter x to represent the radius of the cylinder, I used a slightly more accurate version for that radius when calculating the height. Had I typed in 450 divided by parentheses pi times the rounded version 3.9929 squared, meaning the one that I highlighted here in green by hand, you would get a slightly less accurate answer. And notice my new answer agrees out to the 3rd decimal place, but the 4th decimal place it does not. If you're doing this problem and more, to get credit for the problem, you need to use the full accuracy of the calculator and use the answer 8.9841.